Let's look at the yielding strength of a double angle configuration made of A36 steel. In this problem, we have two angles that are of equal leg length, and they are configured back to back and held in place with 7/8 inch bolts. We have one line of 4 bolts spaced 3 inches apart, and with this, we are going to go to the tables, find an L 4x4 by ½ inch angle, and start to do our calculations. Since we're looking at yielding and we're going to be using LRFD for this problem, we have two equations that we're going to be using to govern through this. We have to find our factored loads that have to be, which we're not doing for this problem, we're just finding the limits. The factored loads have to be less than or equal to the resistance factor times the nominal strength, and this is our design strength. But we have two states for this. If we have yielding, we have PU is less than 0.9, which is our resistance factor for yielding, times Fy times Ag. And then if we're dealing with rupture, we will deal with a similar equation, the same basis, but it's 0.75 as our resistance factor times the ultimate strength times the effective area. So to get through this problem, there's a few things we're going to have to look at. Let's start by finding our gross area. Our gross area can be found from table 1-7, and if we look down a few rows, we will see that our gross area for a 4x4 by ½ inch angle is 3.75 inches squared. Our yield strength, since we're told that it is A36 steel, is going to be 36 KSI, and our ultimate strength can be assumed to be 58 KSI. Now we can start to look at our actual yield strengths. If we're looking at yielding first, we'll see that we have PU is less than or equal to 0.9 times Fy times Ag, and we already have all these ingredients. We have 0.9 times 36 times 3.75. From here, we can simply go to our calculator. 0.9 times 36 times 3.75. We get 121.5 kips. Now we have to go deal with our rupture strength, and this is more complicated. Rupture strength is governed by the same equation to begin with. This is VT/Pn, same, we're still looking for design strength, but when we break this down, we have 0.75 times Fu, which we have, but then we have AE. And you have to understand how to get AE. AE comes from AN times U, and U is our shear lag factor. Once we find our shear lag factor, which for case 2 is what we're looking at here, we have to deal with X bar over L. We can plug this into the equation up here, and area net is another thing that we'll have to find. Area net is going to be equal to the area gross minus the sum of the diameters times the thickness of the material. And this is the diameter of the holes, by the way. So let's start by finding U. U is going to be equal to 1 minus X bar divided by L. X bar is going to be given from table 1-7 as well, because it's a dimensional property, 1-7. And we have, for a 4x4 by ½ inch angle, it is going to be 1.18 inches. L is the length of the connection. So here we have 3 spaces at 3 inches each, which is going to be a 9-inch connection. With this, we can now compute our shear lag factor. 1 minus 1.18 divided by 9 is going to be 0.8689. And this is going to be the most accurate shear lag factor you can come up with. The table will also allow for you to plug in a value of, I believe it would be U is 0.80 for this, but we're not going to do that here. We can review that. That's from table D3-1, I believe. So we have U. Let's now find AN. AN is going to be equal to AG minus the sum of the diameters of the bolt holes times the thicknesses. Now, remember, we're looking at it from this perspective here, right? So, when we go to do this, we have 3.75 still, minus the diameter of the bolt hole. Since we have 7/8 inch bolts, we have 7/8 of an inch plus 1/16 for roughness, plus 1/16 for spacing, which is going to be a 1 inch bolt hole, and we know that it's a 1/2 inch angle. Don't forget to multiply by the thickness. That's caught me up many a time, and it's very frustrating to have to go back to. So now 3.75 minus, that's going to be 1 inch times 1/2 inch will give us 3.25, quite predictably. And now AE, which is equal to AN times U, is going to be 3.25 times U, which I wrote up there, right here. And once we have this, we now have everything that we need. This now comes out to 2.8238 inches squared, and you now have your effective area. So now we can come back to this equation. PU has to be less than or equal to 0.75 times FU times AE. We start plugging things in. We have 0.75 times 58 KSI times 2.8239 inches squared. And that will give us a rupture strength of 122.84 kips. Now we have to look at what's going to govern. Wow, these are extremely close. 121.5 kips for yielding and 122.84 kips for rupture. So actually, yielding is going to govern in this case. But are we quite done yet? Well, not exactly, because remember, this is a double angle situation. So actually, this stress gets to be multiplied by 2. So this 121.5 kips now becomes 243 kips. So it's still going to govern because you would multiply both of these by 2, but yielding governs at a value of 243 kips. So this is a relatively simple problem. I hope you guys found this helpful. You can plug this directly into anything that has to do with an LRFD loading case, and it'll work fine. So if you had, say if we were told that we had a dead load of 25 kips and a live load of 50 kips, you could pretty easily go through and do this, and I highly recommend you actually take the chance to do this, because you can take these, find PU, and then determine if the load is if the member is adequate to carry the load. So this was a very simple review of this type of problem. We didn't go over blocks here in this problem. That's going to be coming up very shortly. But I hope you guys found this helpful, and if you did, please like and subscribe, and we'll see you in the next one.